Well, hello and welcome to the next episode of 3D in 30, How It's Made, the Evolution of Tooling. 3D in 30 is Velo3D's LinkedIn Live and YouTube Live channel. We host this about every 2 weeks or so, depending on the trade show schedule. So make sure you follow Velo3D on LinkedIn in order to get the latest show notes and agenda. So today we're going to be talking about a very cool topic. Got a great speaker. I know everybody saw the card on the intro and you're looking forward to it as much as I am. And if you look at historically speaking, since the invention of the assembly line, the automotive industry has been at the forefront of manufacturing, developing solutions that get copied by industries and companies across the board. And now, in an effort to accelerate manufacturing, lower the cost of delivering an automobile to the public, they're looking at adopting additive manufacturing, but not in the way that you would expect. And that's what's really cool about today's session. So these solutions have taught a lot of best-in-class practices. We hope that this will copy over to plenty of other industries, obviously, being active in the metal additive manufacturing space. And what's different about this is most of the time we think of additive as a solution for low-volume manufacturing. We think of conventional manufacturing, like stamping or casting, a solution for high-volume manufacturing. But what if they're a third category? And what if there's a new area, sort of a gray spot in the middle? And that's what we're uncovering today. We're going to call this AM-enabled manufacturing, where AM is not actually making the end part. AM is enabling the manufacturing of the end part through conventional means. Very cool technology that we're going to go into. So this is a growing category where AM is helping make, in this case, tooling or inserts for the automotive industry. And it's very complex. There's a lot of technology going on into this. And so joining us today, we have an awesome guest. So this is Ante Losic, lead process engineer from Metal AM at General Motors. And we're going to walk through this with Ante today. My name is Mike Roderson. I'm Senior Director of Product Marketing at Velo3D. And this is 3D in 30. As a reminder, this is a live show. We want to hear from you. Please send in your questions at any time. And we'll get to them pretty much as soon as we see them. We like to get to them live, but there can be a little bit of a delay with the system. All right, Ante, let's hear from you. Can you tell us a little bit about your background?
Thanks for having me, Mike. Hi, everybody. As I was introduced as, Ante Losic, I'm the lead process engineer at General Motors. My background in additive stems quite a while now. It's almost been 15 years. I started with polymer printing with SLA and MJM technologies. And then I started a role at Exco Engineering, where I did high-pressure die-cast tooling, specifically around metal additive manufacturing of those tooling components. Everything from printing to simulating and executing those components and seeing how they were able to enable our conventional manufacturing strategies and make them better. And since then, I've joined General Motors in the past 3 years. And there I've been able to utilize my experience in both polymers and metals to look at where we should go next in the machines. And truly, how do we industrialize in the automotive sense machines like these such that they're ready for the factories that we need them to and the volumes that we need them to. So a very exciting time in the world, a lot of hype around additive manufacturing, and really excited to be able to talk to more of these details today with yourselves.
Yeah, I think part of the excitement about this is just the size of the opportunity. I want to talk about that a little bit. In your experience working with additive and then working with additive-enabled manufacturing, how would you compare the two in terms of where they play a role and then relative size?
Yeah, people, when they think of additive and automotive, the first thing that comes to mind is how do I print something and I put it in a vehicle? How do I replace a conventional manufacturing stream? So whether that may be a part that was cast or stamped or injection molded or made in a plethora of other ways, what we can do with additive is make it additively. And so the thought is, well, can I print that component and just do a one-to-one replacement? But the challenge in automotive, which a lot of the other industries don't have, is that we're very cost sensitive. And so to have an additive component that's 10 or 100 times more expensive than an equivalent stamped component makes it a challenge to incorporate in a vehicle, even for all the other benefits that we can have. Also, when we talk about the volumes automotive has, it's millions of cars per year that General Motors makes. And so how are you able to meet those volume needs and cost needs at the same time? So what instead has happened is we've had a lot of success on lower volume programs or variant programs where you're able to create components additively that are cheaper than conventional manufacturing because of the volume need there. So examples can include things like the Celestiq that we announced as General Motors with 115 additive components on board. We also have the Cadillac Blackwing shift knob emblems and other components on those Blackwing vehicles. Here we found that niche area where a direct print additive component makes sense. But that's very small fish. We want to get into every pickup truck, every SUV, every EV on the road that we make. How are we going to get there? And while we fight that challenge of getting to higher throughputs with technologies and looking forward to what's next, we have to think about not just the parts, but the parts that make the parts. And I think that's where tooling has the biggest impact. If you're able to make one or two very high quality pieces of tooling, that piece can then help make the millions of components it makes per year of a higher quality or at a quicker cycle time. And that's what drives its adoption across the industry. That's really where we've seen the most success to date as a company and as an industry on using additive as overall as a tooling enabler to make conventional manufacturing cheaper, better, faster, everything we can think of.
Yeah, you got a nice graph. Maybe we could probably walk through this one a little bit here. You sort of see the typical cost to quantity slopes that we're used to seeing. And then we have this orange line up here, which I'm familiar with in the additive space. It's pretty flat, which is unique. And you lay them one on top of the other and you get some interesting outcomes, but you also have a new regime that with this dotted line.
Yeah, the dotted line is really the home run in all those high volume applications, whether they be casting or molding or whatever that may be, to the millions of components per year. What you're able to do is find ways to use additive to make these tools perform better. And so what that could be as simple of, and what we have a lot of experience with as additive printing, is conformal cooling. So in the world of die casting, we can make conformal cooling channels inside of our inserts, and that'll help cool the casting mold a lot faster, and that enables you to get better quality castings, and they can come out of the machines a lot faster. So that whole regime, as we go to even larger and larger volumes, that's where we see additive being a huge enabler to make it easier for us to make those components, and again, making them faster and better.
So I like this graph because on the left-hand side, additive makes the parts. On the right-hand side, as you mentioned, we make the parts that make the parts.
And there's a little zone in between, but we're gonna fight to try and close that gap so additive is in every part of the process.
I like that. That's awesome. Now it also goes well, sort of, and introducing the complexity of it. So I like this graph here. Volume over there on the left, and then kind of part complexity, and talking about where additive fits in. And I think that low volume, what we talked about before, kind of on the left-hand side there, being replaced at some point in time with stamping and casting. This has been additive for 30 years. This is the prototyping. This is why the system's all sort of had that project work legacy to it. And now we've got more complex parts. And this is where we get introduced to things like the conformal cooling channels now.
Yeah, and obviously everybody wants to be in that top right corner. How can I get the most complex part possible and make 10 million of them a year? And that's going to be a challenge. We're going to continue to push with all our technologies, not just additive. How do we reach into those spaces to make parts that are on vehicles that are performing better than what we can traditionally manufacture? In the meantime, those bubbles are really where AM has a sweet spot right now.
Well, let's dive a little bit, kind of talked about the market there. Very cool opportunity. Looks like it's going to be a very large potential opportunity for additive. So what makes it work? What makes it tick? So what, as an engineer, are you trying to get this part to do that it couldn't do normally?
Yeah, I think one of the big things is maybe understanding what die casting is to explain that example best. So from a basic perspective, think of an ice cube tray or any mold you would have made when you were growing up. You have two halves of a mold traditionally, and you're going to fill it with some type of material. Maybe it's molten aluminum, and then you're going to wait for that molten aluminum to solidify. And when it's fully solidified, you can open it up and take your casting out. And you repeat that process every 1 or 2 minutes, depending on what the casting is. But the critical part's really that third section where you're cooling it. If you're using conventional manufacturing methods, those lines that feed the cooling lines, they're very simplistic. They're straight gun drilled holes, or they're little loops that you make with lots of plugs that can only reach certain areas of a tool. But what you want to do is be able to use conformal cooling and additive to put the water where you need it. So instead of a very blocky line, you can get something that's spiralized and gets exactly to where you need it. So with this now being possible, tools look much more complex. Only without having to put in hundreds of individual spot coolers that are cooling individual areas, you can form very intricate circuits, simplify the plumbing on the tools, all while getting the water to where it needs to be. And what that means is when you look at a casting in general, there's always going to be areas that are thicker or some areas that are thinner, and you're just waiting to open that tool. If you can open it sooner, you're going to get more castings out of the process. Over a year, that's a significant amount of extra castings. So with additive, we're targeting those hot spots, as we call them, or areas where we have thicker aluminum, or just problem areas in general, and delivering the water very close to the surface in a controlled manner, such that you have more thermal control over your entire tool. And what that means in the end, all those things we talked about before: lower cycle time, higher quality castings because the porosity is being moved away to areas we aren't concerned about. And overall, we're getting a tool that functions better. And so that's specific to high pressure die casting, but the same can be said for injection molding and a lot of the other high volume conventional manufacturing streams. We're enabling geometries you couldn't normally cast or mold, and we're enabling parts of the scale that we want to with these additively manufactured tools.
So let's put some numbers kind of around this. I know the answer is always it depends, but how long are you looking at in general, on average, for this process to take place? From 1 to 4, I think there's the 4-step process on the slide.
Yeah. So 1 actually happens extremely quickly. The aluminum's injected in milliseconds. And then by the time you get to 3, that's where we're waiting for a significant amount of time. So a 1 or 2 minute cycle time on a general part, that could be 30, 40, 50 seconds of just waiting for the part to solidify before you can pop it out. And so what does that mean? If I can cool it faster, I might shave off 1, 2, 3 seconds. And while that seems like a very small, inconsequential number, if you take 1, 2, 3 seconds over the course of running this continuously all year round, that's tens of thousands of extra castings you can make off one tool in a year, not even counting the fact that they're going to be a better quality casting and that your tool is going to have a longer lifetime if all things are designed optimally. And so that's by itself, that 1%, 2% increase in decrease in cycle time. That's a huge driver for why we continue to do this on all of our tools in the die casting world.
So just to simplify the math, you've got something that takes about 100 seconds. What you're looking to do with this technology is get a couple seconds back, add that up over the life of the tool, and make that money where that 1 to 2% is worth a tremendous amount of value.
Exactly. And that's where we're suddenly an aerospace customer. Everyone sees automotive as how do you get to millions of parts per year? But in the tooling world, we only need 1, 2, 3 very high quality components. And so suddenly we become like building a rocket. You're only going to build a couple of them, but they better be the best thing you've ever built before. Same idea with the tool. You don't want it to fail early. You want this to last as long as possible. And so those shot counts of how many times it can make a mold before it eventually breaks are very critical. And we want to be able to reach as high a number as possible. So conventionally, maybe you reach 60 or 100,000 shots on a regular non-additive tool. And we want to get to those same numbers or higher with additive. And the reason why, you don't want to have to open up the tool prematurely and take out broken components. That's shutting down machines. That's losing capacity. So we want to be able to get to as high a lifetime on those inserts as possible.
Yeah, so I think we talked about this yesterday in the rehearsal. Our CEO, Benny Bueller, has a slide. It's what's the value of 1%? And it kind of gets into that idea for aerospace. 1% better specific impulse might get you to orbit versus not getting to orbit. In energy, 1% better turnaround time to get a part back in there gets $1 billion facility back up and running. And in most cases, we think 1% for automotive, like 1% more horsepower on a 200 horsepower car. It's kind of in that rounding error. So you don't necessarily print the parts. But now on your side of things, when you're making the parts that make the parts, that 1% now becomes massively valuable again.
You got it spot on.
No, that's pretty odd. And yeah, like what you said, it starts to put it into where the aerospace industry starts to look at things. Yeah. Now, you did mention making the parts higher quality and something about porosity. I'd like to dive into that a little bit. That was kind of a curious comment.
Yeah. So when people think of the casting process for parts in your car, you imagine it's some fully dense part that has no pores or defects inside of it. But if anyone takes a part out of their car that's been cast and goes to CT scan it, you're going to find pores everywhere. It's just inherent to the casting process. As aluminum flows, air is going to be trapped inside. And our whole job as tooling engineers at companies is, how do I move those pores to somewhere it's not going to cause a problem? And that's another big driver of why we use additive in tooling, specifically in die casting. We're able to cool a part of a tool much faster, form a thicker skin of aluminum before everything is solidified. And in essence, you're moving that trapped air pocket somewhere where it's not going to be detrimental to the performance of that component. So it's a very niche area, very hard for most people to understand, but it's a big driver for how do we make programs. When you get a casting the first time off a machine, it may not function the way the simulation ran. And we're using additive as a way to address those concerns and sometimes even save programs by being able to move those pores to somewhere where it's not going to affect the lifetime or the value or the running of that casting.
Okay, so you're getting faster, you're improving the quality of the part, and you mentioned trying to get more shots out of these inserts than you could conventionally. So sort of this trifecta of getting everything you want.
It's almost too good to be true. If someone's just listening in from a layman's side, so in every way it's better. So why is every tool not made additively? And it's a really great question. And the real answer is we're just limited right now. The largest metal AM machines in the world, they're just not big enough to make the tools that we want them to be. So I think if you have an idea of how big a tool is, that changes the scope of it. So people think of an engine block, that's something that's cast. That's a couple 100 millimeters in size in each dimension. Even some of the larger things like transmission cases or structural components, or all the things that we're putting into EVs that are cast, from housing units to battery trays to even more structural components, that size seems big, but the tool that's needed to make that component is much larger. So the steel could be multiple meters in X, Y, and Z just to contain in that component. And so some of those areas right now that we address, we put in small AM inserts. And people in the AM industry will be like, well, what's small? Small is 300-400 millimeters. That's small. We want bigger. We want a meter. And it's just not there yet. And we continue to fight for that. We continue to push for that, to be able to make tools larger and larger. That is what's going to enable even better castings and even better cycle times. So that's one of our big reasons why we don't have more and more additive in tooling. Another one is we're still learning. There's still additive tools that fail prematurely. There's things we don't know about the physics and science of how they run in the tools. Something as simple as we've been using more aging steel for a long, long time. Is it the best steel? No, it was not developed as a steel for die casting. But when it became a time for we want to print tools, it was the most appropriate tool steel that was available additively. So we'll continually look at and analyze all the new tool steels in the market that could increase the life and performance of the existing tools. And then the way we actually print them. Printing something that big is not easy. People make large, big additive parts in aluminum or titanium that are very intricate and beautiful. But a tool insert is a big hunking block of steel. And so to print that whole thing is very, very difficult. It puts a lot of stress on the machine. And even the channels inside, we're limited to how big we can make those channels before they start collapsing in on themselves. And so all of those are drivers to where the next generation of machines are. And as GM, we continue to push for that machine of the future. How can we make a machine that's more appropriate for the tooling market and all these applications that we have?
Yeah, we've got a couple images on the channels you mentioned. Looks like 5 millimeters. You're starting to see some deviation at the top of the channel away from that green circle there, which I guess would be the ideal geometry, right?
Yeah, so depending on the machine and how much time you put into your process parameters and what special features your printer has, the bigger you make that circle, the harder and harder it is to actually close the circle. Just like a traditional welding over nothing is not possible. So in this sense, the bigger the circle gets, the harder it is to close that circle up and the more it deviates from ideal. And so traditionally we see limits of 6, 7, 8 millimeters before it just getting too rough. And too rough means you have stress concentrators at all that roughness, and that leads to premature cracking in your tools and eventual failure. So what we've been able to do through some of the machines that we've brought into our additive industrialization center, like the Velo Sapphires, is use some of that process control, some of the higher power lasers, some of the special techniques like the non-contact recoder to make bigger and bigger channels. So now channels can be 10, 15, 20, 25 bigger millimeters. And what that means is a bigger cooling line can flow more water through it, can cool the casting even faster, and it can make the process even better. So that's where we continue to push. And we've been working with Velo specifically on that. How do we make bigger channels and even more efficient cooling strategies in our existing tooling?
Yeah, we've got a couple questions here. I'm going to take a look at the questions. I'll definitely get to those. Let me ask one question though before we get to that. As like when you're seeing these channels and the closure, you mentioned cracking, and I know I don't know that this was the exact failure mechanism for this channel, but this kind of gives you an example. What happens when you see this type of failure mode?
So every tool, especially in the die casting world, eventually breaks. It sees 600 Celsius aluminum on one side. It sees cold water in the channel. Regardless, additively or not, that thermal gradient and that cycling back and forth every minute or two is massive. And so all those stresses continue to build up until eventually you get a crack form from the casting surface down to the water line, and the water line leaks. And you have to shut the machine off and replace the tool. With additive, if the surface isn't smooth enough, you're going to have that crack start propagating much sooner, and it'll lead to the tool failing at a much earlier point in its life than it would have had if it was a conventionally manufactured tool. And so that's where trying to get as smooth a surface as possible, as close to an ideal circle as possible, is paramount in making sure these massive, expensive tools last as long as we want them to last and longer in our production environments.
And that was part of what attracted you to looking at a solution like Velo 3D at the beginning?
That when we went to the first couple of trade shows a few years ago and saw some of the impellers and some of the crazy geometries that have been printed without any support structure, that was what was motivating us towards trying it out on those machines, because there's no way to remove the supports from a conformal cooling channel. It's buried inside a big block of steel. So you better make as good a line as you can possibly make on day one in order to feel confident that it's going to work in production.
Well, we do have a couple questions here. Let me jump to this. There's a LinkedIn user says, can Ante comment on the use of additive molds for forming parts at high volumes versus existing traditional manufacturing processes, and maybe comparing, maybe without cooling or with conventionally manufactured cooling, and then looking at additive cooling, looking at all three. That could be an interesting way to break that question down. Says the native conformal cooling and heating benefits completely change how metal molds are designed and produced. In this case, it mentions plastic molding.
Yeah, so injection molding is one area where, unfortunately, we haven't had as much penetration as we have with die casting. And I attribute that to die casting is dirty, complex, and traditionally has a much lower OEE, or overall equipment effectiveness, as injection molding does. The molding process, they've been at it for a long time, and typically those molds run for very long lifetimes and make components very reliably, and the tools last a long time. So the benefits of cooling a little bit faster, they are harder to come to than in die casting, where the tools are running at a very low rate to begin with comparative to injection molding. And so we're able to have much more, a much larger impact at a much quicker turnaround with additive manufacturing in those realms. Doesn't mean we're not trying there. There's still features in injection molding that suffer from warpage and distortion and areas that we have lifters or other tools that are problematic for conventional manufacturing. And that's where additive can step in and has stepped in globally, just not nearly at the scale of what it has done for die casting. And then for forming is a little bit even more complicated because we're not specifically thermally limited in what we're forming, maybe in a hot stamping application, but the geometries and shapes we're making are very simplistic traditionally. And so the benefit of a conformal cooling line over a straight drilled line is very, very minute. So it's almost easier to stick to the conventional manufacturing realm there. And we're instead using other additive techniques to try and improve life of more conventional tools there in other ways that are not powder bed fusion. But I kind of hope that addresses all the different caveats in that question.
Yeah, and Kevin, kind of to get to your question, what technologies are we talking about regarding AM? This is a laser powder bed fusion technology, and that's, let me show one of the printers here. So this is the Velo 3D printer. This would be the Sapphire XC. That's what this is called. So that kind of gets into the 600 millimeter diameter versus up to 1 meter in Z height. But basically with this process, you're laying, actually Ante can describe the process as well as I can. So, how does this process work?
Basically lay sequential layers of metal powders, and then you bring a laser in or multiple lasers to melt the specific areas you want in 2D slices. And then you stack those slices one on the other. The benefit with the laser is that it penetrates down multiple layers. So it's binding the layers together instead of just trying to glue one layer to the next. So you get a fully dense structure, or as close to a fully dense structure as you can get with additive with a metal technology like this. So powder bed fusion, big driver for what we're doing. There's other ones too. There's layered object manufacturing. There's DED, directed energy deposition. But in terms of making these conformal cooling channels and to have the full complexity and as smooth a finish as possible, powder bed fusion is really the 99% application space for what tools are made with today in the die casting and injection molding world for this use case.
There's a nice question here regarding removing the powder after the part completes. And I was wondering if you could comment on that. I think that's a pretty good observation, because once you have this giant part, which you're talking about, you got all these intricate channels. Because of the way the process is done, those channels are now full of metal powder. So what do you do to get the powder out?
Yeah, so one side that's unfortunate is that when you're printing big tools like these, you typically are printing the back side with the opening of the holes attached to the build plate. And so you don't have access to those holes every time. You could pre-drill the build plate. You can put little escape channels out the side, but they're not as efficient. And it's very hard for a very long conformal cooling channel to get all the powder out. So traditionally, we just cut the part off the plate right away. And then with the powder stuck in the holes, we'll put in a compressed air line and actually blow out that powder out the other end with all the safety considerations in place of an explosion-proof vacuum, downdraft tables, and having all the right PPE in place for the operators to be protected from that blowing powder. But given those considerations and being able to design the lines such that you don't have, for example, branching inside the lines, that helps to ensure that you get all of the powder out. And frankly, we've been doing this for almost a decade now. And I think we've driven to a place where it's not really become a problem anymore for us in making these tools.
Have you experimented any with the vibrating type of depowdering technologies?
Yeah, so some of the ones you see where you put the plate or the parts on a machine and you shake all the powder out, very possible to do. But given that we're already going to be cutting the part off of the build plate, it's quicker to just add an airline and blow it out. You'll be done your 3 channels in about 30 seconds to a minute. Whereas the time to set it up in a machine, run the process, and then extract the part is actually quite longer. So while those machines are great for open access parts like giant rocket nozzles and unpacking them quickly, it doesn't have the same benefits as it does in the tooling world right now.
Okay. Yeah. And just as a note, kind of Kevin, to your point, what technology is this? So if you're comparing this to something like an E-beam where you might have some cake powder inside, this powder is fully reflowable. So, if you were to take the part after printing, you could just see the powder pour out. It comes out pretty easily. So it's not going to be stuck inside of there or centered in there. There's a question here for regarding supply chain, and I think this is actually kind of good. you kind of mentioned, and I'll summarize it. It's a long question. Let's see, it tends to be a barrier for suppliers investing in the technology because there's just not supply chain supporting it. I know sometimes the intent for an OEM like yourself is to maybe experiment with these systems, but not necessarily own them. You want to have a supply chain network that you go to get the parts. So maybe if you can comment on GM's strategy there, and then what you're seeing in the supply chain space.
Sure. So I'll get to the two parts. I think I got the second part of the question there as well on the material side, but supply chain wise, additive is a whole new area where a lot of what's made currently is through our supplier network. There's a lot of shops out there that have the expertise to manufacture components. And I came in my background from one of those suppliers at Exco, where we would print and deliver those additive manufactured components. Those suppliers took it upon themselves to invest in these advanced manufacturing systems on their own with the hope that they would pan out into a benefit to the company. And they have. And that's where we've been very lucky with some of our big suppliers that they see the benefits that this has. Even though we're still very early on and comparatively to what subtractive manufacturing has done, we see those benefits and they're investing in them, even though it is an expensive process to buy multi-million-dollar machines and facilities to do these processes correctly. Our role at my portion of GM is at the Additive Industrialization Center. We're finding ways to work with OEMs like Velo and others to bring machines in and industrialize them so that they're easier for our suppliers to adopt, and that when they do adopt them, they're able to accelerate very rapidly from first print to production parts off of their machines to what standards GM holds for those components. And then from a material side to the question, it's definitely true. We can only print with certain materials, and they typically are not the same materials we make our existing tools with. Yep. You know, die casting tools are traditionally made out of H13, and people print it here and there, but realistically, most of the tools we print additively for this application are aging steel. And I mentioned it before, it's not the optimal material. So we continue to find ways to try and find new materials that are better suited to it. And in injection molding, the same scenario can be had for, well, we usually make things out of P20 or some other steel. If we really need an area to be colder, we might use Mold Max or some kind of copper, brass alloy to pull out heat. But with this conformal cooling, we can control that a bit more because you can time your water and control when it's going to start solidifying and when you stop solidifying. So there's a bit more process control that the process engineer on the floor is going to love to be able to make a higher quality mold. But we're going to continue to find new materials, find things that match better, such that our suppliers don't have to suffer with doing all this homework on their own, because it is a very expensive process. And companies like GM and others are investing in it so that we don't just better ourselves, but the industry as a whole improves.
No, that's a great way to kind of wrap it up too. I think we're beyond the 30-minute mark. I do want to mention one thing here. We have a white paper. If you're interested in learning more, we just launched this not too long ago, a couple of weeks ago, how additive manufacturing is transforming tooling. It breaks down a lot of what we've talked about today in a little bit more detail. So if you're interested in learning more about Velo3D's experience in the tooling industry, heavily inspired by Ante's teachings. So definitely he's been a great voice for us here at Velo3D. Hopefully he's been an awesome voice for our audience today. So Ante, I want to thank you for coming on the show, and everyone who attended today, thank you for joining. Any final words to close us out?
I just want to keep everyone in mind that additive is going to continually change. Things are going to get better, faster, larger. We're going to continue to drive for that with all of our partners and with all the people that we work with. And we're just looking forward to more people adopting this, getting used to it. And if there's ever any questions or any thoughts or things that you think that might change the mold again, bring them forward. It all started with a couple of people taking a stab in the dark that this is going to work. And it turned into this huge business, and it's only going to continue to accelerate.
Awesome. Great job. And if you're interested in seeing more content like this, make sure you follow Velo3D on LinkedIn. Follow General Motors too, because you're going to see some really cool automobiles coming pretty soon. And that's a wrap for us today. So stay tuned for more shows.
Thank you very much, everyone. Thanks, Mike.